thank you for coming for this lecture, and we will continue from the last lecture, well foundation. And when we talk about in the well foundation in the introductory part, one last part which was on the forces, and when we talk about introduction on the well foundation, one of the issue was forces acting on the wells. We will talk about that before talking about the lateral stability of the well foundation. So, when we talk about forces acting on wells, these are the list of the forces. In addition to the dead load and live load, well is also subjected to following forces: wind force or seismic force. Then you have force due to water current, force due to movement of vehicle, temperature, earth pressure, buoyancy and centrifugal. These are the list, and there could be many others also. So, what you have? You have a combination of these forces. N stand for the normal case. Normal case will be treated when it is subjected to all forces except two, that is seismic and thermal temperature. So, that means because the normally beside out of wind or seismic force, only one of them need to be considered. If you are considering the wind force, then seismic force will not be considered. If seismic force is considered, then wind force will not be considered. So, this about this aspect you may be already aware. Then forces due to water current, that is if it is applicable, then it need to be considered in any case. Then because the wells are mostly designed for the bridges, the forces due to movement of vehicle need to be considered. Then temperature force, which may be optional in the sense that if there is a variation in the temperature, then it required to be considered. Earth pressure will be always considered in the design. Buoyancy will also come, if it is coming, then centrifugal force. So, what we have here, the T stand for the temperature, S stand for the seismic forces. So, for N plus T, permissible stress is normally should be increased by 15%. If you are considering seismic forces, then the permissible stresses are increased by 25%, and if both thermal as well as seismic is considered, then permissible stresses are increased by 50%. So, what we can say that in this list you have temperature, and out of this is seismic. So, beside this list, so this list you have all minus A minus D is your N. So, that if you are considering all forces except what is listed in A and D, then this will be the normal force. Then the next one, the force acting on wells. In this slide, the combination has been shown here. So, what you have three equations which are satisfying the conditions of equilibrium, that is summation of V equal to 0, H equal to 0 and M equal to 0. So, what you have here, so you could see here you have the well, and on that on the top of this you could have some pier which is shown here. So, what you have here, the well is embedded inside the soil. So, this is ground level and this is D is depth of well. Okay. From the depth of the well, the point of action of the forces, the height have the H. So, total height from the base of the well is to the point of action is H plus D. Okay. And what are the forces acting on the well? Forces acting, vertical forces W, then horizontal force also acting on this. These horizontal force may be due to many reasons, it could be due to water, it could be earth pressure, it could be your seismic load or wind load. So, these are there. So, P and Q are two components of the horizontal forces, because in the horizontal you have two direction, this direction and this direction. So, in one direction it is P, in another direction Q. So, altogether this well is subjected to three forces, one vertical and two horizontal force. Now, under these three forces, let us in this figure the force system is shown for the two dimensional case when you are considering the one vertical and one horizontal component Q acting on this well. All these forces are acting at a height H, where height H is from the like you have this is level, ground level. So, here this level is shifted here to this point. Now, you have D plus H is acting. So, what you have 3 equations satisfying the conditions of equilibrium, summation V equal to 0 and the total downward force W base reaction plus friction on the side summation H equal to 0. So, altogether total vertical forces should be 0 and total horizontal forces should be 0. So, this is 2 equilibrium equation. The third one equilibrium equation comes from the moment equilibrium forces, where what you have all the moments acting should be 0. So, in the first one vertical will be related to the what you have for summation V equal to 0, weight W plus friction force on the side. Weight will act downward, friction force will act upward. Summation of H equal to 0 is simply saying the lateral force Q equal to 0 and this is equal to net lateral earth pressure including friction at the base. And summation of M equal to 0 is simply Q multiplied by H plus D, where Q is the force, horizontal force, and H plus D is your this height. So, the sum of the moments due to net lateral earth pressure, friction on both sides and base reaction. So, this is the system which is showing, and let me again say about this one that what you have on the vertical force W is acting downward and the soil reaction is acting upward, that is there, and this reaction could be from the base as well as from the side. Same thing when you apply the lateral load, then soil from the side try to provide the reactions support, and that support should be considered as a opposite to the in the direction of the motion. So, this all these 3 equilibrium are considered in this forcing system, and with that we are going ahead for that what is the like lateral stability of the valves. This is very important for the earthquake point of view, as when we discuss pile foundation you may be aware that during the earthquake it is the lateral load which is more important than the vertical load, because the vertical load will be always acting. This is the lateral load which cause or the horizontal force which cause the problem. So, several methods are available and 4 methods are here. One is Tarjagi 1943, then Pender, Banerjee and Gangopadhyay and Indian Road Congress. Tarjagi, the first one and the last one, first and the fourth one we are going to discuss in detail, and thus I will introduce you second and third one. So, let us first talk about Tarjagi. Tarjagi assumed a free ridge bulkhead for lateral stability analysis of valves. Okay. So, first of all they have ridge bulkhead has been considered for lateral stability. Then Pender extended the analysis for Tarjagi. Tarjagi's the soil around the pier was assumed to behave like linear springs. So, where stiffness increased with the depth. So, rather than assuming the constant, that they have replaced the soil assuming that it is a springs. Then next Banerjee and Gangopadhyay utilized the Pender's concept, plastic flow concept, and along with Tarjagi's ridge bulk stress distribution and subgrade modulus concept. Then Indian Road Congress formulated recommendation for valves in cohesionless soil to estimate soil resistance below maximum score depth. So, let us start from Tarjagi's theory and then we will talk about IRC. So, Tarjagi's, which is very well known and very famous and quite old, starting from 1943. When a ridge valve sand deposit moves parallel to its original position, the sand on the front face of the valve is transferred into a passive state, whereas into the rear face it is transferred into an active state. So, you have 2 cases, one is passive, another is active state. So, what you have the front face, what happens, suppose like you see here in this case, let us go back to this one. So, if you move to the valve, then in the direction when the valve is moving this direction, the soil here will push and this passive resistance will develop this soil, while active resistance will develop on another side. So, you have both sides of the soil. So, one part of the soil where it is pushing, it will go in the passive action, the soil which is pulling, getting pulled will be under active pressure. So, you have both the conditions generated when the valve moves, passive as well as active conditions. So, that valve is transferred a passive state, whereas in the rear face it is transferred into the active state. Thus, when the passive and active pressure are fully developed, the net resultant pressure Pz at any depth is given by this gamma z into Kp minus Ka, where gamma is unit weight of soil and Kp is coefficient of passive earth pressure and Ka is coefficient of active earth pressure. So, equation 1 give you the value of Pz net resultant pressure at any depth Z. The next continue with that, considering a free ridge bulkhead in a sand deposit, the bulkhead is considered free if it owes its stability solely to the lateral resistance of the earth adjoining its buried part. So, the stability is, it will be considered free if its stability is coming due to the lateral resistance which is provided by the soil under the buried part. The bulkhead with an embedment depth d is subjected to horizontal force q. As the magnitude of the horizontal force increases gradually, the bulkhead tends to rotate about certain point O above the lower edge of the bulkhead, and at failure the soil is in a state of plastic equilibrium. So, what has been said is can be explained from this figure. Here you have a bulkhead. So, here you, as we already discussed, capital D in all the well foundation which we are using is the depth of the well foundation. It is not the diameter of the well foundation. So, this is the one point we need to understand. So, capital D is the depth of the well foundation and force Q is acting at a height h. When this force Q is acting at height h, this will try to pull, you know that this, and the well will try to rotate. This rotation, if it is completely raised, fully raised, then the point of rotation will be at the at the base, at the bottom. It is very heavy or raised. However, due to, because this height and then this you have total height h plus d. H is the point of action where your forces are acting, which we have already discussed when we talk about forces. Then, so what you have this this is the point O shown here, this point O. This point O is the point of rotation where the bulk get try to rotate. It is shown at the that failure the, so the bulkhead tends to rotate about certain point O above the lower edge of the bulkhead, and at the failure the soil is in a state of plastic equilibrium. So, what is done? Q is this force shown here. You keep increasing the value of Q. When Q start increasing and the value of Q becomes higher, then this will try to rotate, and this will once it get then if you increase the value of Q will reach to a maximum value, what is called Q max. Q max is the value where it will get the failed, and we need to determine that value. For determining this value, we need to consider both force and moment equilibrium. So, what is done? The resistance offered by the soil can be approximated by the pressure diagram, as it can be seen, and Q max is area of pressure diagram. In this diagram, if you see E H B, E is this point, H B one side, and on then because this point of rotation is here. So, the another triangle F H B, which you can see F H G, this from here to here. So, as shown area of pressure diagram. So, when we work on this area, half gamma d square Kp minus Ka, and another one is where we assume, let us say what is d1, d1 is the height of this triangle, that is from base to the point F. When you have from this equation can be simplified. So, equation 2 you get Q max equal to half gamma d Kp minus Ka into d minus twice d1. Then you have equation 1 we already discussed, this was the force given in equation 1, then equation 2 is here. Now, after this equation, if we have the moment equilibrium, so in the moment equilibrium you provide you another equation where Q max into H plus d is the moment which is caused by this load, and resistance is coming from the soil, which is from these two triangles. First one will be multiplied by d by 3 and the second one d1 by 3. So, ultimately you get equation 3. Now, what is done? If we substitute the value of Q max from equation 2 to in equation 3, then we are able to get the value of d1. See that in this case, in this problem, what is the issue, that we do not know what is the value of d1. If we are able to know that d1, then you can locate that this fulcrum, or this is the point of rotation O. So, this can be located. So, if d1 is known, then rest of the calculations are done. So, for finding the value of d1 we are trying to have here. So, first thing is that substitute the value of q max from equation 2 to equation 3 and you end up here. After substituting and you get cancelled from both sides. So, ultimately after substituting you get this equation. Now, in this equation is d1 is unknown and this d1 to find the value of d1. So, our objective is to find the value of d1 and for d1 for finding this d1 this is the quadratic equation and this is written in this form and ultimately if you solve this equation then you can get the value of d1 finally obtained from this equation. And you need to understand that h1 in this equation is nothing but h1 is known which is h plus d. So, this is the case here and h is the height here not the horizontal force which I use here. So, h is the height from the ground level to the point of action of your forces. Okay. So, once h1 is known, d is known then you can find the value of d1. Thus, d1 can be found from the equation 4 and substitute the value of d1 and if you substitute the back in equation 2 the value of d1 then you can get the value of q max, that is the maximum force acting. Then continue with this. What the Tarjagi theory yield conservative results as it neglects friction at the base and the sides. So, this is the it says that though there is a friction between the base of the valve and the soil. So, this is neglected by the Tarjagi's theory as well as in the side. If surrounding soil is submerged then submerged unit weight of soil should be used for q max. A heavy valve under a lateral load will rotate about the base. The value of q max can be computed by taking moments about the base. So, what you have q max if we have instead of if the point of rotation instead of point O, if point of rotation is at point B, in that case rather than the q max can be obtained from equation number 5 directly. And there may be situation there could be unscored soil depth up to the bed level and its influence can also be taken into account if you by considering earth pressure due to surcharge. So, if you have Z is equivalent surcharge height which is due to unscored soil depth then this Z should be added in equation 5 to get the value of q max. So, the equation 5 is modified if you have additional surcharge where d square into d plus z is divided by the h plus d. So, instead of 1 multiplication of d it will be d plus z. So, this was the case. So, ultimately what is there? So, equation 4, 5, 6 gives you the value of q max depending on the case. 4 will give you the value of d1 and you substitute back in equation 2 you will get the value of for this case value of q max. Otherwise, if your point of rotation is at the base then directly equation 5 can or 6 can be used. Okay. So, let us assume that value of q max is known. Once the value of q max is known, so for a valve with length L or diameter equal to L, the maximum force q max is q max into L given from this equation 7, where L is nothing but length or diameter of the valve. So, this can be obtained like this. Then you have this once this q max is known, now the allowable load or allowable the horizontal force q a can be calculated from equation 8, where what is the difference between 7 and 8, that simply you are dividing value of q max by a factor of safety f, and usually for valve foundation the factor of safety f is greater than or equal to 2. If the applied horizontal force on the valve is q and the allowable equivalent force is q a, if you are putting a load on the valve which is more than the allowable the value q a, then an unbalanced horizontal force will be generated and this will create an additional moment. So, if your the load is more than the allowable then additional moment will be coming and that need to be taken into further analysis and design. So, this additional moment can be there. This is permissible that q value may be higher than q a because for q a is obtained using factor of safety, but naturally let us say if you are using a factor of safety 2, the value of q cannot be 2 times or more than that for the value of q a. So, what you have is additional overturning moment m b which is due to this q is greater than q a, this is given by equation 9. Now, once m b is known, the total weight of the valve is known coming on the top, then you can find the maximum and minimum foundation pressure at the base, which is given from equation 10. Maximum value naturally will come plus sign, and if you use the minus sign you will get the minimum value, and these values should be less than the permissible stresses. So, maximum net direct load on the base of the valve after taking into account the buoyancy and skin friction, A is the area and ZB is the section modulus of the well base. So, this is not well wall, this is well base. So, this should be well base. So, you have this. Now, once you have this, so what you can have, this is in these two cases the maximum value should be less than the permissible value and minimum should not be tensile, it should not be 0. So, this is the case. Continue with the Tarjagi's theory, the maximum foundation pressure should be less than the allowable bearing pressure, and the wall standing is subjected to bending moment due to the horizontal load Q, which is we already calculated, and the maximum bending moment in the standing occurs where the resultant shear force is 0. As you know that BM bending moment will be maximum where the shear force is 0. So, what is done? The point where the shear force is 0 can be located using equation 11. Equation 11 gives you the point where the shear force is 0. So, once x is known, then we can find the maximum bending moment using equation 12 where mx q into h plus x, and x is obtained from equation 11 and you get the maximum bending moment. And if the applied moment at a score level is m, then also in another way you can find the value of maximum moment using equation 30. So, equation maximum bending moment can be either found equation 12 or 13 as the case is applicable. So, this was all about Tarjagi's theory. Now, let us little bit discuss what Pender have suggested. The Pender proposed an analysis for lateral stability of wells, and two different types of wells, namely light and heavy wells, were considered by the Pender. The sandy soil around the well was assumed to behave as a linear spring with stiffness increasing with the depth. So, how the soil is characterized? It is soil is using the linear springs, and it is assumed that stiffness of these springs are increasing with the depth. In a heavy well, friction was assumed to develop at the base, whereas in the case of light well, no friction was assumed to develop at the base. There are two cases, one is heavy, another is light well as the. So, heavy well is okay because at the base frictional forces are considered, while in case of light well it is assumed that there is no friction. So, in case of heavy well, the well will rotate about the base, while in case of light well the point of rotation will be little above the base. So, which is expected like this. Equation satisfying the condition of steady equilibrium was solved with the soil modulus obtained in terms of Rankine's earth pressure coefficient using the concept of imminent plastic condition at the surface. So, this was the like concept of the Pender's theory. Then Banerjee and Gangopadhyay, what they did, they combined Tarjagi and Pender's concept and then proposed in 1947 that the plastic flow concept and the bulkhead stress subground modulus concept. They proposed an analysis for the lateral stability of the valve. The analysis was developed for a valve in sandy soil. All like 4 theories which we are discussing are basically for granular soils or cohesionless soils or the sandy soils. 2 cases were considered, a general case with no plastic flow and second case with partial plastic flow was considered. The equation for the various forces acting on the valve were worked out and the condition for equilibriums was satisfied, and modification for heavy valves with rotation about the base have also been suggested by Banerjee and Gangopadhyay. So, this was the case. So, with this introduction on Pender's concept and Banerjee and Gangopadhyay, we continue with the last one, that is IRC method, the Indian Road Congress method, and that is this is called in short IRC method also for the lateral stability of the valves. And lateral stability of the valve, which is very important during earthquake motion, this is also provided by the passive resistance of the soil on its side and base. So, this is basically passive resistance. The resistance developed at working loads is different than at ultimate load. So, there is a document of IRC, IRC 45 1972, and what has been recommended by this document, that it recommended elastic theory method. There are ultimate theory method and elastic theory method. So, we are going to talk about today only elastic theory method to estimate the soil pressure on the side and the base under design load and ultimate soil resistance for actual factor of safety against shear failure. So, you have 2 cases. One case is estimate the soil on the side, estimate the soil pressure on the side and the base under design load. So, you have under design load and under ultimate soil resistance on actual factor of safety against shear failure. So, when you are considering the shear failure, then ultimate soil resistance will be considered. This is applicable for non-cohesive soils like sand and surrounded by some soil below maximum score level. The recommendation will not apply if the depth of embedment is less than 0.5 times the width of the foundation. So, foundation in the direction of lateral force. So, that means the value of D should be at least greater than 0.5 times of the B, where B is the minimum dimension of the valve. So, this is the case. So, continue with this IRC method. In IRC there are two theories, one is elastic theory method, another is ultimate soil resistance method. So, we are going to discuss today only elastic theory method. In case of elastic theory methods, these are the assumptions in IRC methods. The assumptions made in the elastic theory method are: the soil surrounding the valve and below the base is perfectly elastic, homogeneous and follows Hooke's law. So, this is the first condition, that whatever soil you have, what is the soil you have below surrounding the valve as well as below, it is perfectly elastic. Under design load, the lateral deflections are so small that the unit soil reaction P increases linearly with increasing lateral deflection Z, such that P is equal to Kh into Z, where Kh is the coefficient of horizontal subgradation at base. And so, this is, that means if you increase the value of Z, the value of P is going to increase, and Kh the horizontal subgrade reaction. This also depends on the type of soil. So, if you have the sandy soil or granular soils, the value of Kh is also normally considered to be linearly increasing with the depth, and this coefficient of horizontal subgrade reaction linearly increases with the depth in cohesionless soil, as we discussed. The valve behaves as a rigid body and act upon by directional horizontal force H and a moment M at its core level. So, what is valve is subjected to force H as well as moment M. Be careful, H is also used for the height. In the case of when we discuss Tarjagi's theory, H was the height of the forces acting from the ground level, while in this case in elastic theory method, H is the horizontal force and moment M. So, now these are the steps in the calculations. The first steps: having determined the minimum grip length, the applied loads and moments are calculated. So, what are the loads acting? Three loads are acting. One is a total downward load acting to the base of the valve. Second is H is horizontal force acting on the valve at core level. So, H is here not height, rather H is the horizontal force acting here, and M is total applied moment about the base of the valve, including those due to tilts and shifts. So, you have three forces, one vertical, one horizontal and one moment. So, these are the forces which may be known coming on the whatever transfer from the piers and this. So, using the valve dimensions, calculate the following geometrical properties. What are the geometrical properties? Two moment of inertia need to be calculated. One is said IB and another is IV. So, IB is moment of inertia of the base about an axis passing through the center of gravity and perpendicular to the horizontal resultant force, and this moment of inertia which is about an axis passing through the center. So, what you have here, let us say that if we go in our this, so this let me show one figure, what this mean by this here. So, this is the case here. So, this is your picture well in the elevation. So, the axis which is passing through the center and H acting is here is core level, this H is acting like this. So, horizontal force if it is acting in this direction, this will be the vertical axis will be acting, because this is perpendicular to the lateral load. So, this is the case here. So, IB is moment of inertia of the base about an axis passing through the CG of and perpendicular horizontal resultant force, and this is given by pi by 64 B4. IV is moment of inertia about the horizontal axis. So, IV is if you draw an horizontal axis which is again passing through the CG and the project area in elevation of the soil mass offering resistance. So, IB is about vertical axis and IV is about horizontal axis, and this is given by LD cube by 12, and I, if we know this IB and IV is known, then IBI, the moment of inertia can be calculated from this relation. Now the issue is this, what is L? D already defined, D, capital D is the depth of the well. So, which is throughout constant, this is not the diameter of the well, that need to be understood. So, D have the depth of the well. So, once now let us see that what are these M, IV, IV and IB is already known, what is mu dash and alpha, where B is the diameter of circular well or width of the base parallel to the direction of the horizontal force. So, we need to understand B is the diameter of the well, not the D. Okay. Normally D is the diameter, but here B is the diameter of the well or width of the base parallel to the direction of the horizontal force. L in this equation is projected width of the well which is in contact with the soil, offering passive resistance multiply by appropriate shape factor. And to find the value of L, this is first of all what you need to have, the first get the projected width of well and then multiply by the shape factor. So, shape factor is 1.9 is recommended for circular wells, while whereas 1 is recommended for square and rectangular wells. So, for rectangular wells L will be as it is as a projected width square or rectangular wells, while in case of circular multiply diameter by 0.9, then you will get the value of L. So, for the circular L is nothing but 0.9 times B, and otherwise for square and rectangular it will be B itself. Then M is ratio of horizontal to vertical coefficients of grade reaction, that is KH and KV. Normally if you have assume for isotropic soil KH and KV is both are same, so this factor will be 1. Then mu prime is coefficient of friction between the sides of the well and the soil, and this mu prime can be obtained as a 10 delta. What is delta here? Delta is friction coefficient between the sides soil and the well. So, you have the well and the side soil, so the friction coefficient is delta. So, once delta is known, mu prime can be known. Then the alpha, which is coming in equation number 1, the alpha is given by B by 2D. Again you need to understand that D is not the diameter here, B by 2, B is your the diameter, divided by 2 will be radius, and then it is divided by the depth of the well. So, that will give the value of alpha. So, alpha is naturally a ratio and dimensionless. So, this way using equation 1 you can find the value of I. Once I is known, then rest of the calculation we start. So, from step 3rd onwards, what is done here, some checks are applied, and I am not going in the derivation of these checks how these equations have come, because they are too complicated. So, rather than we are going to talk we are going to discuss about its application part. So, what is the condition for stability of the well? So, that point of rotation of the well lies at the, this is the well, this is like this, this is a little misprinting, this is the point of the rotation of the well lies at the base by ensuring that the frictional resistance at the base is adequate to restrain the movement of the well. So, this can be ensured if your value of H should be greater than what is given by equation 2A, or H should be less than 2B. You need to understand H is the here horizontal force. So, the relation between horizontal force and moment should be using equation 2A and 2B. So, what is given to you? 3 forces are given, external forces. H is given, horizontal force, W weight of the well is given, and M moment is acting. So, the combination of these 3 forces should satisfy the equation 2A and 2B, both equations should be satisfied. Equation 2A says that the value of H should be the minimum value, equation 2A will provide you the minimum value of H, and equation 2B will provide you the maximum value of H, that the H value of H should be less than this and the value of H should be more than this. So, that means with the help of equation 2A and 2B you can get the range of the value of H, that means the value of H should be more than the particular value and less than that. So, once that range is known, then you check whether your H is within that limit or not. If it is not coming in that limit, naturally you need to revise the design. So, now in these equation 2A and 2B, H, M and W are already known. Mu prime is already defined. Now, what is mu and R? That is defined in the next slide. Mu is here coefficient of friction between the base and the soil. Okay. So, this is the coefficient of friction between the base and the soil. So, this is coefficient is known, that is mu prime was related to, and mu is nothing but tan phi. So, if phi is the angle of internal friction for the soil below the base, then mu equal to tan phi, while delta was the friction between the side soil and the well. While as for R is concerned, R is given from this relation d by 2 I m I v. Again d is the depth of the well, not the diameter. I is known, I v is known, m is known. So, once R is calculated, so in this equation 2a and 2b all things are known, and then we can work on this equation. We can decide what should be the value of H for given value of m and w. This was the first check. The second check for the well foundation says, check that the soil on the sides remain elastic. This can be ensured by keeping the slope of the pressure parabola at the top below the passive line, that is this product m multiplied by capital M divided by I should not be greater than gamma into Kp minus Ka. Gamma is the unit weight of the soil, Kp and Ka are earth pressure coefficients, which is depends just only on the value of one. Kp is passive earth pressure coefficient and Ka is active earth pressure coefficient, and this is the same as we discussed in Tarjagi's theory also. Capital M is the moment, external moment, while small m is not small m is a coefficient ratio, which we have already discussed. This is Kh or Kv, which is normally considered to be 1. So, once you know this equation third, this is another check. So, equation 2a and 2b will be one check, equation third will be another check, but still the checks are not completed. If equation third is satisfied, then we go ahead and check the base pressure, ensuring that the maximum compressive pressure is less than the allowable bearing pressure and the minimum pressure is not tensile. So, what is you calculate the stresses from equation 4, sigma 1 and sigma 2. When you use plus sign, let us say you get the sigma 1, and when you get minus sign you get the sigma 2. The value of sigma 1 should be less than the permissible stress, while the value of sigma 2 should not be 0 and there should not be negative, it can be 0, because no tension should come in picture. So, in the step 5 we will make sure that sigma 1 is less than the permissible value, while sigma 2 is more than equal to 0 or more than 0. So, A is the base area of the well, P is total horizontal reaction from the side, that is m by r. The value of P can be calculated m divided by r, where m is external moment, r is obtained using equation 2c, and then B is width of the base of the well in the plan of bending. So, here P is known, mu prime is known, everything is known, m, b, 2i. So, you can calculate the value of sigma 1 and sigma 2. So, this was the case there. Whatever we have discussed, like that these are the applicable. So, here the first figure is showing you the elevation of the well, which is a circular cross section and cylindrical well, while two other sections, one is showing you deflection profile and pressure distribution at side. So, this is you have the D, where D is the depth of the well, deflection profile, deflection is 0 at the base where the well is that heavy well, and when you go above, deflection is maximum at the ground level, and naturally if you consider the variation linearly, the deflection at any depth y from the ground can be d minus y by theta. So, when here at the point the y is the depth, the y equal to d, capital D, so deflection will become 0 and y equal to 0, here will be simply d, so d into theta, where theta is this angle, theta will be in this case you are this angle theta. Okay. Then you have at any depth the variation sigma x, and what is shown here, this is center of rotation C, and you have a strip is considered for derivation of all the formulation which we have discussed. So, this case is not applicable here. So, continue with this, what the checks which we have applied, the last check especially like condition of stability, that is the equation third. For equation third, if there are two conditions, if the soil remains in elastic state, the minimum soil reaction from the sides cannot exceed the minimum pressure at any depth. This will result in equation third, which we have already discussed, and the next condition is also we discussed, the maximum soil pressure should be at the base, sigma 1 should be less than the allowable bearing pressure, that is the value of sigma 1 should be less than Qa, that is the allowable bearing pressure, and sigma 2 should be greater than or equal to 0. So, this thing is also discussed. So, most of the contents of this slide we have already discussed. So, this was the IRC elastic resistance elastic method, and in this lecture and the last lecture, the references are like this you may be knowing that this lot of things are given in the book by Ranjan, Professor Ranjan and Rao. Then there is a code of practice for IS code on the design and construction of well foundation, that is IS 3955 1967, which is also referred. Then Indian Road Congress document 45 1972 with title Recommendations for Estimating the Resistance of Soil Below the Maximum Score Level in the Design of Well Foundation for Bridges, and this is, I think it is under upgradation. So, when it comes, then this can be the new document can be used with that if it is. So, with this all I thank you very much for your kind attention, and we have discussed all the for the lateral stability of the wells, we have discussed all the 4 theories, and we have discussed in detail 2 of them. One is Tarjagi's method, another is IRC method in detail. Thank you very much for your kind attention. Thanks.